In previous lecture we discussed aldol condensation, and in this lecture I will be discussing to you about Perkin, Claisen and Dieckmann condensation, and this topic comes under chemistry of carbonyl compound under the Calcutta University MSc Chemistry second semester. Coming to Perkin condensation, it is exactly similar to the aldol condensation. Aldol condensation is the addition of enolate or enol of an aldehyde to the carbonyl group of the same aldehyde or ketone or to a non-enolizable carbonyl. Perkin is also similar. In enolate, we are using Perkin acetic anhydride enolate, and this enolate of acetic anhydride added to the non-enolizable carbonyl, that is aromatic aldehyde, usually benzaldehyde for example, in the presence of a weak base. The final product will be alpha beta unsaturated acids. So acetic anhydride, benzaldehyde in presence of weak base sodium acetate, it gives cinnamic acid. This is the example. Coming to the mechanism, and with acetic anhydride in the presence of a weak base, you can get only very low concentration of enolate, because this acetate is not enough to get enough quantity of enolate. This base, strength of base is not enough to get enough quantity of enolate. So this low quantity of enolate will be added to the non-enolizable part, that is benzaldehyde, and it forms an intermediate structure like this, and this is similar to aldehyde. And next step is a different one, an intramolecular acylation reaction occurs. So I redrawn the structure like this, the same structure like this, and this oxy anion intramolecularly added to the carbonyl of the same compound, and it forms an cyclic intermediate. And this tetrahedral cyclic intermediate, in this intermediate, this oxyanion come to this, it form a double bond, and either of this single bond has to break. So next we have to look which one is the best leaving group. This carboxylate is the best leaving group, so it breaks the bond, this single bond, and it form a structure like this. So next step, we have to remove this acetate from here. So acetate is a very good leaving group. Acetate is better leaving group than hydroxyl group. So you remember in aldol reaction final step in unsaturated product, a dehydration occurs. The mechanism was even CV mechanism. Same mechanism is also happens here. There are two routes for the formation of this unsaturated product. Either of this route is okay, and in presence of acetic acid, it forms a protonated structure like this. Then even CB mechanism occurs. In presence of base, this proton is acidic and anion will be formed. Then it enolizes. So it enolizes like this. Then this enolase dehydrate this acetate, deacetylate this compound like this, and it form unsaturated acid. And the second route is also okay for this mechanism. Acidic anhydride, if you use acidic anhydride instead of acid, you get anhydride. Same enolization occurs, and finally this acetate group are removed from this compound and you get unsaturated product. So Perkin reaction is a base catalyzed reaction of an aldehyde having no alpha hydrogen atom with anhydride. Another example, furfural can react with acidic anhydride in presence of base and it give product unsaturated product like this. An application of Perkin condensation, it can be applied for the synthesis of coumarin. Coumarin is an industrially important compound. And this synthesis can be started from salicylaldehyde. Salicylaldehyde can react with acidic anhydride in presence of base and it is a Perkin reaction and it form compound like this. This finally dehydrated. This carboxyl group OH and this hydrogen get dehydrated to give coumarin. So next step, Claisen condensation. It is exactly similar to aldol condensation, only the difference is instead of aldehyde you are using ester. So it is an addition of an enolate of an ester to the carbonyl of same ester. So two esters condense in presence of base to give a beta keto ester. And classic example for the Claisen condensation is the ethyl acetate condensation in presence of base, and finally you get ethyl acetoacetate or acetoacetic ester, this one. And coming to the mechanism, ethyl acetate, this mechanism is similar to aldol condensation. In aldol, first step is the enolate formation. Same like this, in ester, enolate of ester will be formed. This already we seen how this enolate is formed. And in aldol condensation, next step, second step is the addition of enolate to the carbonyl carbon. And the same way, addition of enolate of ester will be added to the next molecule of carbonyl ester and it form an intermediate. And in final step, there is a difference in aldol condensation. Final step is the protonation. And on protonation, this O minus will become hydroxy group. But in this reaction, in Claisen condensation, this actually restores this carbonyl group like this by expelling ethoxide, and it forms finally a beta keto ester. And actually, in the case of Claisen condensation, sodium ethoxide base is not enough to actually to enolate this ethyl ester. But at the same time, this is good enough, strong enough to deprotonate, enolate this, deprotonate this hydrogen atom, because from the pK you can understand that ethoxide pK is 16 and ethyl acetate pK is 25. But ester, this hydrogen's pK is 10 and this is good enough to, ethoxide has good enough to enolate this structure. And finally a stable, very highly stable enolate will be formed. So this product will be formed in excess. But here the enolate formation, you can see this backward reaction is favored. But here, due to the stability of this enolate, this product will be highly in high yield. And finally, this enolate should be hydrolyzed to form beta keto ester. And this is the review problem. You have to do the write the mechanism of the Claisen condensation of ethyl propanate and ethyl butanate in the presence of base. You have to do this both problem. And coming to the Claisen crossed Claisen condensation. In crossed Claisen condensation, we are using one ester is not having an alpha hydrogen atom, not D hydrogen, alpha hydrogen atom, and it can act as an enolate acceptor. So other ester will be enolate forming. This one will be non-enolizable ester. Example for non-enolizable esters are ethyl formate, diethyl carbonate, diethyl ethane thioate, ethyl benzoate. And this is the enolizable part, this is non-enolizable part. In this case, methyl propanoate, enolize, this one enolate, and this will be added to this carbonyl, and this methoxide will be expelled, and finally you get this product. Similarly, in this case, non-enolizable part is ethyl methanoate, and this is the enolizable part. This will be added to here, and you will get this product. And in this example, ethyl phenyl acetate is enolizable part. This will be added to the non-enolizable part, diethyl carbonate, and it forms a structure like this. Next one is Dieckmann condensation. Dieckmann condensation is intramolecular acylation reaction. It is intramolecular Claisen condensation reaction. And classic example is cyclization of diethyl ester of adipic acid. This is adipic acid. This cyclized in the presence of base, and finally it hydrolyzed to give a structure like this. And this is useful for the preparation of 5 and 6 membered ring only because of the ring strength. And coming to the mechanism, it is intramolecular cyclization, and it is a diester of one of the carbonyl of carbonyl form an enolate, and this proton ethoxide remove this alpha hydrogen and it form an enolate, and this enolate attack the carbonyl group at the other end of the chain, and you can see this whole equilibrium favors towards the left, and enolate formation is a very less quantity you can get, and this attack take place at this carbonyl and double bond break and form an intermediate like this, and finally ethoxide will be expelled like this, and this ethoxide and remove the acidic hydrogen located between two carbonyl. This is highly acidic, and this is good enough to remove this proton, and more importantly the formation of this anion, this enolate, it is highly stable because it can form resonance with this carbonyl and this carbonyl. So it form an highly stable enolate, then finally it hydrolyzed to give this beta ketoester. And next example, this compound. In this compound you can see this is the diester in presence of base. It form a 6-membered ring, and here one of this hydrogen, this alpha hydrogen get enolized, and this attack the 7th carbon. So second carbon you can see here, this attack this 7th carbon, okay, this 7th carbon, and this methoxide get expelled. So you get this part here, this part here, and cyclization occurs to 2nd and 7th carbon. Okay, that's all about Dieckmann. This is intramolecular Claisen condensation, and you have to do this question. I have given 4 structures, and you have to tell and what ketoester can be formed by Dieckmann. So determine which one are possible and draw the starting esters of all this final product. That's all. Thank you.